Find the derivatives of the following 8 functions. And here we use the fact that if y equals x to the power r, where r is a real number, then dy by dx equals r times x to the r minus 1. And this result is true for all values of r, positive, negative, 0, integer, or a fraction. So to differentiate x to the r, we write down x to the r, we pull r down to the front as a multiplier, and we subtract 1 from r. Problem 1, y equals x to the 5. So to calculate dy by dx, we write down x to the 5, we pull the 5 down as a multiplier, and we subtract 1 from the index, which gives us 5x to the 5 minus 1, which is 5x to the 4. Problem 2, y equals x to the minus 3. So to find dy by dx, we write down x to the minus 3, we pull down minus 3 as a multiplier, we subtract 1 from the index, so we get minus 3x to the minus 3 minus 1, which equals minus 3x to the minus 4, or minus 3 over x to the 4, using the rules of powers. And having demonstrated the process in some detail for the first 2 problems, we will now continue more quickly. Problem 3, y equals x to the power 3 over 2. So dy by dx equals 3 over 2 x to the power 3 over 2 minus 1, which equals 3 over 2 x to the power 3 over 2 minus 2 over 2, which becomes 3 over 2 x to the power 1/2, and that becomes 3 root x over 2, since x to the power 1/2 equals root x. Problem 4, y equals x to the power minus 1.73. So dy by dx equals minus 1.73 times x to the minus 1.73 minus 1, which equals minus 1.73 times x to the minus 2.73. Problem 5, y equals x to the power pi. So to differentiate x to the power pi, we pull down the pi as a multiplier and we subtract 1 from the power to give us pi x to the pi minus 1, which cannot be simplified any further, because pi is an irrational number which cannot be represented exactly as a fraction. Problem 6, y equals 7. Now y equals 7 is not in the correct form to apply the rule that we are using, so we have to rewrite it into that form to apply the rule. And so we have that y equals 7, which equals 7 times 1, and that means that y equals 7 times x to the power 0, since x to the power 0 equals 1 for all x. And now we can apply the rule in the usual way. We have that dy by dx equals 0, the power, which we pull down, multiplying 7 times x to the power 0 minus 1, which equals 0 because 0 times any real number equals 0. And this result tells us that the gradient of the graph of y equals 7 is 0 everywhere, i.e. it is flat, parallel to the x-axis, which is true for any constant whatsoever. And usually when we differentiate a constant, we recognize that fact and write down its derivative as 0 immediately with no further work. Problem 7, y equals x. And again we recognize that this is not in the correct form to differentiate using the rule, so we rewrite it into the correct form, and we can do that because x equals x to the power 1. And so applying the rule, we have that dy by dx equals 1, the power pulled down as a multiplier, times x to the power 1 minus 1, which equals 1 times x to the power 0, which equals 1 times 1 because x to the 0 is 1 for all x, and 1 times 1 equals 1. Problem 8. y equals the square root of x. And we note once again that this is not in the form required by the rule, but we can rewrite it into the correct form because root x equals x to the power 1/2. And now we apply the rule to find that dy by dx equals 1/2, the power pulled down as a multiplier, times x to the 1/2 minus 1, which becomes 1/2 times x to the power minus 1/2, which becomes 1/2 times x to the power 1/2, using the rules of powers for negative powers, which finally gives us that dy by dx equals 1/2 root x, since root x equals x to the power 1/2.